Okay, in this second video for 7.8 we're going to look at the other type of improper integral called a type 2 improper integral. That's where the integrand, which is the function you're integrating, is not continuous on the closed interval from a to b. Here's the case where the function is not continuous at 0, is it? 1 over square root of x is not continuous at 0. So we define the improper integral kind of like what we did for type 1. We're gonna first define the definite integral from t to 1, and then we're going to compute that definite integral. And then at the very end, we're going to look at what happens as t goes to 0. But we're only looking from one side. We don't care what happens below 0. It only happens when you approach 0 from the right. Graphically, what's going on is we're looking at the area under the curve 1 over square root of x from 0 to 1. You have a vertical asymptote here. It seems from the graph that the area under the curve is obviously, it's not clear, is it? This is where your intuition might fail. So let's just let calculus take care of that, okay? So we do the integration. So you get 2x to the 1/2 evaluated from t to 1. Make sure you keep your limit sign on every single step. So when you evaluate it, you get, let's factor the 2 out. Square root of 1 is 1 minus the square root of t. Now you take the limit as t goes to 0. This factor goes to 0, so the answer is 2. So it turns out the area under the curve from the vertical asymptote to 1 is actually 2. It's finite. Amazing. Here's one where the function, the integrand 1 over x minus 2 is not continuous at the upper limit of integration. So you'd write it like this. It's the limit as x goes to 2 of the integral from 0 to t of dx over x minus 2. Graphically, we're talking about if this exists, if this improper integral exists, it would be a negative number, wouldn't it? From 0 to the vertical asymptote at 2, this is certainly going to be a negative quantity. It's not clear whether or not it would converge or not, though. So again, we're going to let calculus take care of that for us. We're going to first compute the definite integral, get the natural log absolute value of x minus 2 from 0 to t. Then we're going to evaluate the limits of integration here. So ln of absolute value t minus 2 minus ln of 2. As t goes to 2, though, from values less than 2, you see what's happening, folks? This right here inside is getting close to 0, isn't it? As x, this is actually a t, not an x. These should be t's, right? Anyway, this thing inside the absolute, inside the natural log is getting close to 0. So what happens to the natural log as what you give it gets close to 0? It goes to negative infinity. So this is a case where you get a divergent improper integral. Okay, on this one we're looking at the integral from 0 to 1 of the natural log of x dx. Again, so this is an improper integral of type 2 because the integrand is not continuous at 0, right? It's got a vertical asymptote. So we define it like this. It's a limit as t goes to 0 from values above, the definite integral from t to 1 of ln of x dx. And let's see, let's do a little side work here. We've done this before, I'm sure. What is the integral of the ln of x? That's a very simple integration by parts, isn't it? You'd let u equal ln of x, so du is dx over x. Then you let dv equal dx, so v equals x. So you get uv minus the integral of v du, which becomes v du. The x is cancelled, so you just get dx. Anyway, so this is your answer. It should be plus c. We don't care because we're going to be doing a definite integral, but the indefinite integral should be x ln of x minus x plus c. Okay, so back to the problem now. So when you do the integration, you get this expression evaluated between t and 1. Of course, its limit as t goes to 0, plus of that. So you end up with this. Look, you get when you plug in 1, this becomes 0 minus 1, and when you plug in t, this becomes t ln of t minus t. And it's not obvious what this is getting close to as t gets close to 0. That's a little L'Hopital's rule there. It turns out that limit is 0, but here's why. The limit as t goes to 0 plus of t ln of t has the form 0 times infinity. So So you could bring the t down and write it as ln of t over 1 over t. Now it has form infinity over infinity. Apply L'Hopital's rule to that. And so this becomes 1 over t on top, negative 1 over t squared on the bottom. If you flip this over, bring it on the numerator, you get negative t. So as t goes to 0, it's actually 0 plus, but it's still 0. So therefore this limit goes to 0. This limit obviously goes to 0. So your answer is negative 1. So what does that say? What that says is if you look at the area under the area under the x-axis, we should say, of the natural log function from 0 to 1, this area is finite. In fact, it equals negative 1. Amazing. I would not have guessed that. Let's do another one. How about this one? What's the problem here, if any? This is the integral from 0 to pi over 2 of secant x dx. Well, it'd be nice to remember what the secant function looks like. It's the reciprocal of the cosine, right? So from 0 to pi over 2, the area is the shaded portion. This is my cosine, so this would be the secant. So it's the shaded portion. What do you think? You think this is infinite or finite? I'm going to guess infinite, although I cheated. I looked at this. I actually did this problem, so I know. I'm going to say infinite. Anyway, let's see. We're going to write it as the limit as t goes to pi over 2 from values less than pi over 2, right? Of 0 to t of secant x dx. The secant of x is pretty easy to compute, isn't it? It's just going to be the natural log of the absolute value of secant plus tangent from 0 to t. So when you plug everything in, you get the limit as t goes to pi over 2 from below, ln secant t plus tangent t in absolute values, minus the ln of secant 0 plus tangent of 0. Now, secant of 0 is 1. Tangent of 0 is 0, so this last term just drops out. But anyway, what is the as t? This is where you have to look at the graph. As t gets close to pi over 2, you got a serious problem in here. It's pretty obvious that the secant is going close to infinity, right, from this graph. But also the tangent is too. So this is actually getting close to infinity plus infinity inside. So this whole thing, the natural log, is also getting close to infinity. So that's why the answer is it diverges. We'd say it's infinite area. Okay? All right. Now, it's also possible to have a problem of continuity somewhere in the middle between the a and b. In this case, this function 1 over x minus 1 is not continuous at x equal 1. So what do you do there? Well, the way we define it is we define it as the improper integral from 0 to 1 of dx over x minus 1 plus the improper integral from 1 to 2 of dx over x minus 1. And both of these integrals have to converge for the whole thing to converge. So if you can show that one of them diverges, then you don't have to show the other one diverges. I'm going to look at I1. I1 is going to be, it's not continuous at the upper limit, so we're going to write this as the limit as t goes to 1 from below of 0 to t dx over x minus 1. So the integral is easy to compute. It's just natural log absolute value x minus 1. The limit as t goes to 1 below of ln x absolute value x minus 1 from 0 to t. And when you plug in the limits of integration, you get limit as t goes to 1 below of ln absolute value t minus 1 minus ln of 1, which is just 0, right? So what is the limit? As t gets close to 1 from below, notice this thing inside the ln is getting close to 0, so the ln function gets close to negative infinity. That's why the integral diverges. All right, I got one for you to try. Try this one. See if you can do this last one here. Okay, this one you're going to have to use integration. Let's look at let's use integration by parts here. And I'm going to just show this to you because we don't have much time. But when you use integration by parts, you get this. So then when you plug it back in, you get this evaluated between t and 4. You get this, but again, you're going to have a issue. It's not clear what the limit as t goes to 0 plus of square root of t ln of t. So you have to apply L'Hopital's rule. It's kind of a little separate thing. You show that limit equals 0. And so anyway, getting back to the problem then, the limit as t goes to 0 plus, when you plug in the limits of integration, you should have gotten 4 ln of 4 minus 8, and these both go to 0, so this should have been your answer, 4 ln of 4 minus 8. Alright, we'll see you next time. Bye-bye.